Have you ever wondered if the universe has an edge? What would happen if you got in the fastest spaceship imaginable and just kept going in one direction? Would you eventually bump into a giant wall that says universe ends here? It's a question that keeps astronomers up at night. We look out into the cosmos with our powerful telescopes seeing galaxies billions of light years away, and it seems to go on forever. But forever is a tricky concept. What if the universe is playing a clever trick on us? What if it's both infinite and has a specific shape all at the same time? It sounds like a riddle, but it's one of the most profound ideas in all of science. This idea challenges everything we think we know about space. We are used to things having clear boundaries. A box has sides, a ball has a surface. Even our planet is a big round sphere with a definite size. So let's get back to our spaceship. You're cruising through the cosmos, past shimmering nebulae, ancient galaxies. You are determined to find the edge. You travel for billions of years faster than light itself. You keep going, expecting to see something different, some sign you're close to the end, but you never do. The view always looks roughly the same, an endless tapestry of galaxies and vast stretches of cold, dark space. This is what we mean when we say the universe might be infinite. It has no center and no edge. This idea ties directly to the Big Bang. Many picture the Big Bang as an explosion in space, like a bomb in a room, but that's not quite right. The Big Bang was an explosion of space itself. To understand how the universe can have a shape, we need to distinguish between two different ideas, local curvature and global topology. These sound complicated, but the idea is simple. Local curvature is something we can measure. It describes the geometry in our observable patch of the universe. Flat, like a piece of paper. Positively curved, like a sphere. Negatively curved, like a saddle. Each geometry follows different rules. On a flat sheet, triangle angles add to 180 degrees. That's Euclidean geometry. On a sphere, a great circle triangle between three cities, angles add to more than 180 degrees. Scientists look for these effects in the cosmos. CMB measurements suggest the universe is remarkably flat. That might suggest an infinite flat plane. But flat doesn't have to mean infinite. This is where global topology comes in. To really wrap our heads around this, let's take a trip to a famous imaginary place called Flatland. Flatland is a universe that exists only in two dimensions, like a giant endless sheet of paper. The beings who live there are simple shapes, squares, triangles, circles. They can move left, right, forward, backward, but they have no concept of up or down. They can't even imagine a third dimension. Now imagine we as three-dimensional beings reach down and gently fold their universe. Let's take their flat plane and connect its edges to form a cylinder. For the Flatlanders, nothing seems to have changed. Their world is still locally flat everywhere they look. Triangles still add to 180 degrees. But something profound has happened to the global shape of their reality. Now if a Flatlander travels far enough in one specific direction, they will circle around and return to their starting point. We could take their cylinder and bend it around in our third dimension, connecting the ends to form the surface of a donut, a torus. Again, from the Flatlanders' perspective, their world remains perfectly flat. They have no way of perceiving the curve we created in the third dimension. This is the perfect analogy for our own situation. We could be living on a 3D manifold that loops in a higher dimension. There's another twist in this cosmic story. Even if the universe is truly infinite, our view of it is not. There is a fundamental limit to how far we can see. The cosmic horizon. This isn't a physical wall or an edge in space, it's a boundary in time. The universe is about 13.8 billion years old, so light from the most distant objects has had only 13.8 billion years to travel and reach our telescopes. Anything farther than that, the light hasn't had enough time to arrive. We are surrounded by a personal bubble of observability. Every observer in every galaxy has their own cosmic horizon, their own personal bubble. It's like being on a ship in the middle of a vast ocean. You can see to the horizon in every direction, but there's more ocean beyond it. Based on light travel time and expanding space, the diameter of our observable universe is about 93 billion light-years. That's an astonishing volume, filled with at least 2 trillion galaxies. But it may be only a tiny fraction of the whole thing. The true universe could be hundreds larger, thousands larger, infinitely larger. It's a humbling thought, a reminder of our small place in the cosmos. If we can't see beyond our cosmic horizon, how can we ever hope to figure out the global shape of the universe? Are we doomed to forever guess? Not quite. Astronomers are clever. They've come up with ingenious ways to search for clues that the universe might be finite and wrapped around on itself. The main idea: search for repeating patterns in the sky. Imagine a donut-like topology. Light from one distant galaxy could take multiple paths to us. One path, the direct straight-line route. Another path, the long way around. Light could loop across the universe and arrive from a completely different direction. That would make the same galaxy appear in two different places in the sky. A cosmic echo, a ghost image. The looped path traveled further, so we'd see the galaxy at an earlier time, but the best place to search isn't galaxy maps. It's the cosmic microwave background, the CMB. The CMB is a snapshot from when the universe was about 380,000 years old, a glowing wall of plasma filling the sky. If the universe is finite and connected, these CMB patterns should repeat, like a hall of mirrors. Scientists run supercomputers to scan CMB maps for matching circle pairs. So far, the search has come up empty, no definitive repeating patterns. The data favors either a truly infinite universe or a universe so large that repeats lie beyond our horizon. When we put all the evidence and theory together, cosmologists are left with three main possibilities for the ultimate fate and shape of our universe. These possibilities are tied to the universe's overall density, basically how much stuff is packed into it, matter, energy. This density determines the curvature of spacetime. The critical density is the precise amount of stuff needed to make the universe perfectly flat. The first possibility is a closed universe. If the universe's density is greater than the critical density, space is positively curved, like the surface of a sphere, finite in size but with no edge. Gravity could eventually halt expansion and pull everything back together in a big crunch. Observations currently suggest this is unlikely. The second possibility is an open universe. If the density is less than critical, space is negatively curved, like a saddle, and it is infinite. Expansion continues forever. Stars burn out, galaxies drift away, a big freeze or heat death. The third possibility is a flat universe, what our best measurements currently support. In a flat universe, space is flat and likely infinite. But the discovery of dark energy, accelerating expansion, complicates this. A flat, dark energy-dominated cosmos will also expand forever, leading to a cold, empty future. So the fate of the cosmos hangs on density, greater than, equal to, or less than the critical value, closed, flat, or open. Our data currently points toward flat, likely infinite. But dark energy makes the future stranger than the simple textbook cases. The work continues. Let's return to that video game analogy. It's one of the best ways to visualize what a flat but finite universe might feel like. Imagine you're the hero in a classic two-dimensional adventure game. You can move up, down, left, right. When you walk off the right edge of the screen, you don't hit a wall, you instantly reappear on the left edge. Your world is a torus. It's a perfectly flat playing field, but it's also finite. You could measure its total area. You can map the whole thing. Now let's upgrade this game to 3 dimensions. You're flying a spaceship through a cube-shaped universe. If you fly through the right wall, you reappear from the left. Through the top, you come in the bottom. Front to back as well. This is a 3 torus. You could look in one direction with a powerful telescope, and if the universe were small enough, you would see the back of your own head. Of course, the light would have taken a very long time. You'd see it as it was billions of years ago. The sky would be filled with repeating patterns, a cosmic hall of mirrors, showing the same structures over and over. The fact we haven't found them means, if the universe wraps, the wraparound distance must be larger than our observable universe. The screen is just enormous. So, what is the final shape of the universe? The honest answer is, we don't know for sure. The cosmos keeps its grandest secrets well hidden. Our current evidence points toward a flat universe, one that is either truly infinite, or so unimaginably vast it appears infinite to us. But the idea that we might live in a finite, looping cosmos, a donut or a wilder manifold, remains tantalizing. The absence of evidence isn't evidence of absence. Telescopes and supercomputers keep pushing the limits of our knowledge. The search goes on, and the best part is, you can be part of this exploration. Keep asking questions, keep looking up. This mystery ties the smallest particles to the largest structures, a puzzle written in the ancient light of the Big Bang itself. The next great discovery could come from anywhere, sparked by a mind that dares to wonder. If you enjoyed this journey into the mind-bending shape of reality, please subscribe to our channel, give this video a thumbs up, and share it with someone else who loves to wonder. There's a whole universe out there waiting for us. Let's explore it together. The cosmos is calling. I hope you'll answer.